Hi, thanks for coming. So I'll be talking about polynomial identity testing. My name is Amit Sinhababu, and here is my email ID. If you have any further questions, you may email me at this address. So I chose this topic for a couple of reasons. One is, this is a basic question in computer science that has some applications in algorithms also. Also, there is some interesting complexity theory aspects of about this problem, and furthermore, many Indian computer scientists have contributed to this problem, and among them is my supervisor, Professor Nitin Saxena from IIT Kanpur, and his advisor, Manindra Agarwal, who is also from IIT Kanpur. So, let me begin with the problem. So, we know about polynomial identities from school algebra. So, we know that this is an identity, and how do you prove that this is an identity, right? So what you can do is you can expand it out completely, right? And this term cancels, and you get x square minus y square. So this is how you prove identities in school. Now, yeah, in this question also, basically you will be given two polynomial expressions in n variables, say p x1 to xn and q x1 to xn. The task is to check if p equals to q. Now you can bring q to the other side and equivalently test if p minus q is identically 0, right? So now you may think that we can always algorithmically decide if p minus q equals to 0, because we can expand out all the monomials and check monomial by monomial if each coefficient is 0, right? But that would not be an efficient solution. I will show later why it is not efficient. So basically the point I want to make here is how these p and q polynomials are given to you as input. That is important. Like if it is given in an expanded form, then this problem is trivial. But if it is given in a form where you have to do the expansion and check, then this becomes non-trivial. So the question is how the polynomial. So now I will be talking about only one polynomial because I brought the other polynomial to the left hand side. How the polynomial is given, and for that we have to fix sort of a data structure about representing polynomials, and yeah, I'll start with univariate polynomials. So take an univariate polynomial a0 plus a1x plus a2 x square plus an x to the power n. So you can like represent it in this form, right? Like you can give all the monomials and its corresponding coefficients. So let me ask you one question, like suppose I give you this polynomial, how many additions and multiplications you need to evaluate this polynomial at a given point? So for example, like here for computing an x to the power n, you may use n many additions and multiplications.
No, like n multiplication. Because you need to multiply x into x into x.
Yes, I think you
Oh yeah,
yeah, you can like you need, yeah, you are right, to compute x to the power n we do not need that. Okay, let me like still like, yeah, but anyway, like so basically one way to answer this question could have been this, that for computing n to the power x to the power n, you need n multiplication, then n minus 1, x to the n minus 1, you need n minus 1, and then for a1 x, you need 1 multiplications. And in total, that would have been like 1 plus n, so n times n plus 2, roughly n square many multiplications, right? But you can actually compute it using just n multiplications. So let me tell you how. So this is called Horner's rule. So basically it is grouping, so a0 plus x you take out, and then a1 plus x, then a2 x an. So you can check that these two polynomials are same, right? This is another way to compute this polynomial.
You can also pre-compute all powers of x, right?
Yeah, we can pre-compute all powers of x, but like this, that would not be more efficient than this. Okay, so you basically need kind of like n additions and n multiplications. I might be off by 1, like it can be maybe n plus 1, or, and it has been proved that this is optimal. You cannot like, so if I ask you to write a program like where all these coefficients are given as input, a0, a1, an, and a given value alpha, and then evaluate this polynomial at the point alpha, you cannot like do it better than n additions and n multiplications. But in special cases you can improve. So that is the case that some of you were telling about. It is the x to the power n, right? Like this is the idea of repeated squaring or binary exponentiation. So this I think all of you know. So the idea is like you compute x and x square, x to the power 4, x to the power 8, and so on, right? So basically you need around log n many multiplications. Now what about 1 plus x square plus x to the power n?
Can you do it with the geometric series and with like division?
Yes, you are right. So this expression is like x to the n plus 1 minus 1 by x minus 1, right? So this obviously you can use repeated squaring to compute the numerator, but there is a division involved. So that is a bit like of an issue. But you can think about this. This I am giving as an exercise. You can also compute this polynomial using order log n many additions and multiplications. Should I give you some hint? Okay. Yeah, you can try to think about it. Couple of things are obviously like you can say take n to be some power of 2, try to group it in a way so that like divide and conquer kind of strategy. You know about how to compute Fibonacci numbers efficiently, right, using matrix exponentiation. You can also try to bring that idea here. Another idea would have been obviously to eliminate this division somehow. That is also possible. So there are at least 3 ways to do this, and let me not go into that now. But you cannot expect that every polynomial can be like of not every polynomial of degree d, not every polynomial, univariate polynomial of degree d can be computed in using polynomial in log d many additions and multiplication. Okay. So this actually you can prove like such polynomials exist. Okay, it's like but you do not know of a single polynomial for which you can prove this fact. This is like the P versus NP question. Okay. So for example, let me give you these polynomial x plus 1 times x plus 2 times x plus d. How many additions and multiplications you need to compute these? Okay. So for this, the conjecture is you need big omega of d many additions and multiplications. Huh? Omega, big omega is the, like, you need at least say d many, I mean, of the order. Okay, you know about the big O and big omega notation. Lower bound. Lower bound. Okay, no. Yes, so basically, like, so one thing you can see from here is, like, if suppose you can compute this product in polylog d, right, then you can put, say, without division, okay, and then you can put x equals to 0, and that will compute d factorial, right. So d factorial in polylog d, that actually is unlikely, okay, we do not know. So basically exponentiation versus factorial, right, is not known. And in fact, this is also an elementary exercise that so I am giving too many exercises. Another exercise is, suppose you can compute n factorial in polylog n many operations. Then integer factoring can be solved efficiently. So you can think about this. I think with your knowledge you would be able to solve this exercise. Okay, so now I move on from univariate to multivariate polynomials. So where the variables can be any arbitrary number n, and then how many additions and multiplications you need to compute multivariate polynomials, that is the question. So here also you can see, so basically the point I want to make here is, like, yeah, so again, like, you can, so n variate degree d polynomial can have n plus d choose d many monomials. So this is a basic counting exercise, and this expression is, like, can show that it is mean of less than equal to mean of n to the power d and d to the power n. So unless n is constant or d is constant, there are exponentially many monomials for general n variate degree d polynomial. So if you want to encode this as a, like, all the monomials is an array, right, like all the monomials, all possible monomials, and you basically in this array you keep their, you order them in some order, say lexicographic order, and then put the coefficients. So that will be a too large expression, right. So a better way to represent polynomials is possibly you represent via trees. So you say start from variables x1, x2, xn, you sometimes you add them, then you multiply them, and you can, the scalar multiplications you can, like, in the edges you can have some scalar values, say alpha 1, alpha 2, okay, and so on, right. And then actually, so this is a directed tree, rooted tree, and so in each node a polynomial would be computed, right, and at the root node the polynomial that will be computed, yeah, so say that is a polynomial p x1 to xn, okay. So these things are called arithmetic formulas. So instead of addition and multiplication gate, if you use Boolean and or gates, and if these variables are Boolean variables, then that is a Boolean formula. but here it is computing a polynomial. So it's a arithmetic formula. And then you can see that actually these formulas can compute, like for example take 1 plus x1 times 1 plus x2 times 1 plus xn. Right? So how many monomials it has? Huh? 2 to the n, right. It has 2 to the power n many monomials. But to write it as a tree, it will require only order n size, right? But has order n size arithmetic formula. Okay. So you can also, instead of trees, you can be a bit more relaxed and use directed acyclic graphs. They are called circuits. So here you can, in the tree case, the out degree of each node, addition or multiplication, that was restricted to be only 1. Okay. But here you can reuse. Okay. So reuse of computation is allowed. So for example, this repeated squaring example, right? X, there we use the power of reusing it, right? We are, every time we are squaring it, so we are reusing the computation. So the circuits, like obviously trees are a special case of this. So this can be like even more powerful in terms of like reducing the number of additions and multiplications. So yeah, so the point is like you can use formulas and circuits as data structures for representing polynomials. So suppose you want to solve a problem, algorithmic problem involving polynomials, and then you can like think of that the input representation is like this. Okay, like if you are given two formulas, then you can add them, right? You can multiply them. So you can do operations like this. And if you are given a polynomial in these formats, formulas or circuits, then evaluation is efficient, right? Evaluation can be done efficiently if the size of the formula or circuit is small, right? Yeah. Okay. So now I come to, but again, like I told in the univariate case, not every polynomial would have small formula or circuit. Okay, like.
By the way, is there a name for algorithm which can compute the circuit or the arithmetic formulas data structure or something?
No. So basically you are asking about like whether given a multivariate polynomial, how do I come up with the smallest circuit that computes it?
Yeah.
So that might be a hard problem. Okay. Okay.
There must be approximators or.
No, that is a hard problem.
Not even approximate.
Yes. But you can imagine, like say suppose you want to, let me tell you a problem, like you want to factorize a multivariate polynomial, right? And you want to try out like all possible polynomials, right? So you can basically imagine that you are like working with circuits, and in all possible ways you are filling up these variables, constants, and then that will kind of like, yeah, basically the input you can imagine to be already given in this format. Okay, and then you can try to use this representation to solve the problem. So now I again come to polynomial identity testing. So we can be little more precise now. So given an arithmetic formula or circuit, test if the polynomial computed by the formula or circuit is identically 0. Okay. Now you already saw an example like this 1 plus x1 times 1 plus x2 times 1 plus xn, where expanding would have led to 2 to the power n many monomials, exponentially many monomials. So expanding this brute force solution is definitely not efficient. So is it an easy problem? Like yesterday's lecture you heard about P, NP. So is it in P? Is it in NP? Is it NP complete? So you may kind of try to relate it with this problem unset, right? Like in the Boolean setting, if you are given a Boolean formula, like is there a, like it's like, so it's identically 0 means there is no satisfying assignment, right? Like that is unsatisfiable, and that is hard. That is like in the class co-NP, right? That is, but actually like in this case, you might be surprised to know that this is not expected to be hard. It is expected to be in P. It is not yet known, but actually there is a solution that involves a new idea, that is using randomness. Okay. So what is the idea? It's very simple. So basically like the algorithm is, these are called randomized algorithms. So peak, so take a set, finite set S, which is a subset of the rational numbers. Peak numbers alpha 1, alpha 2, alpha n uniformly and independently at random from S, and test if the given polynomial, so the input is say is a circuit C x1 to xn, which is computing. Test if C alpha 1 to alpha n is 0. So if it is non-zero, so if non-zero, then you definitely know that the polynomial is non-zero. You basically output non-zero. If it is 0, then what would you do?
Try again until
Yeah, so if it is 0, then you just output 0, output identically 0. So obviously you are thinking that this might be mistaken, right? This decision may not be correct, but so that is why for this kind of randomized algorithms you have to estimate the error probability. Like what is the probability that actually this was non-zero polynomial, but because you unfortunately picked a bad point, it turned out to be 0. And obviously, as you said, that by repeating the experiment, we can then hope to reduce the error probability. And there is a way to formalize this. This is called Schwarz-Zippel lemma, but it turned out like it was discovered even before in some other form. And this says that so this is generalization of this familiar fact that any non-zero polynomial, univariate polynomial fx of degree d, and fx you assume that over a field f. You know what is a field? Where It is like, you can think of it as like rational numbers, complex numbers, where you can add, multiply, subtract and divide. Any non-zero polynomial fx of degree d has at most d roots. Okay. So if you take a set S, say take set S, and you pick a random value alpha from S, then the probability that f of alpha is 0, take random alpha from S, probability f of alpha is 0 has to be less than equal to d by cardinality of S, because there can be at most d roots. And amazingly, the same bound would hold if you do it for multivariate also. Okay. So that is the statement of the Schwarz-Zippel lemma. It says that
Isn't this also the fundamental theorem of algebra?
yeah, so fundamental theorem of algebra would say that if you are working over an algebraically closed field like complex numbers, then there are d roots, right? But this is actually even easier to prove. This you can prove using factor theorem, right? That you learned in school, that if f of alpha is 0, then that implies x minus alpha divides fx, right? So using these you can prove that there are at most d roots. You do not need fundamental theorem of algebra to prove this.
I was thinking, like, isn't it, doesn't this just follow from the.
It will follow from obviously fundamental theorem. Okay, so yeah, so basically like the statement for the multivariate case is this, that so take again any set, take any finite set S which is subset of the field elements, and then pick alpha 1, alpha n uniformly and independently at random from S. So you are given a non-zero polynomial, f x1 to xn. So probability f alpha 1 to alpha n is 0. So probability, like when these alpha 1 to alpha n are picked uniform and independent at random from S, would also be upper bounded by d by cardinality of S. Okay. So if you take S to be say cardinality of S is 2d, then this will be less than half, right? So how do you prove such a statement? Any idea? Yes, exactly. So univariate case you already saw. So that is the then obviously you would try to reduce to the univariate case when you are trying to do the bivariate. So natural idea is induction on the number of variables. Right? So when you try to prove things about polynomials, there are two important things: degree and number of variables. You could also try inducting on the degree and first try to analyze the linear case and so on. But in this case, because like the univariate case is easy to understand, it's more natural to try inducting on the degree. So let me quickly give you the proof. Yeah, assuming I didn't prove the univariate case completely, just gave the hint that it follows from this factor theorem. You can try to fill in the details. So here the idea is this polynomial f x1, x2, xn. So you can write it in terms of, so imagine we are trying to work out the inductive case, right? Inductive step. So you can write it as a polynomial of, say, of this form. Say it will look like, say, phi x1 xn minus 1 times xn to the power r plus if let us write fr then xn times f1 and then say f0 x1 to xn. So what I did is I separated out one variable xn and tried to express this polynomial as an univariate polynomial in xn, but obviously then the coefficients are themselves polynomials in other variables, right. So this is like, so the n variate case you have to reduce to n minus 1 variate case, right. So this is a natural way to split the polynomial so that you can hope to prove such a thing, right. So now if this polynomial has total degree d, then this polynomial has degree d minus r, right, this coefficient. So this xn to the power r, so this has degree d minus r, total degree is d. So now the way it can be 0 at a random point alpha 1 to alpha n 1, it can be like, you can think of, you are substituting some alpha 1 to alpha n minus 1 first, okay. First you substitute alpha 1 to alpha n minus 1 and then this coefficient, it may vanish or it may remain non-zero, right. So you can branch out by, so suppose this so it can be, one case is this is non-zero, another case is this is 0. Then the whole then the evaluation, like it can be, if it is non-zero, but after that, after we substitute in alpha n in xn, it can be 0, right. So it is like conditional probability, right, in this. So after that, like if it is non-zero, then it can happen that f of alpha 1 to alpha n can be 0 conditioned on this event that this was non-zero, right. And similarly here, if it is 0, then also you have to prove that estimate the probability that after that, when you substitute alpha n, then also it remains 0, right. These are the two ways it can be 0. So we are splitting the event in like these two paths, right. So what is the probability of this, that fr alpha 1 to alpha n minus 1 is 0. So this is, here you can use the inductive hypothesis, right. So like this is like same as, so this had degree d minus r. So this is like, this probability is less than or equal to d minus r by cardinality of s. And okay, this, what is the upper bound of this? Okay, yeah, so let us ignore, yeah, 1 minus something. And then assuming this is non-zero, then it is an univariate polynomial of degree r, right. So that probability will be, this probability will be less than or equal to r by cardinality of s, right. So these two are kind of like coming out to be more complicated expressions, but probabilities are always upper bounded by 1. So here in this branch you give 1, in this branch also you give 1. So in total the probability will be less than or equal to r plus d minus r by cardinality of s, so less than or equal to d by cardinality of s, okay. Okay, so but you can also try to play with the proof, like this is one way to decompose this. Can you decompose it in other ways, right? Like you are seeing this as an univariate polynomial over the rest of the variables. Can you see it as a say polynomial like in x1 to xn minus 1 whose coefficients are coming from the polynomials in xn? You can also split it in the other way, right? Even in that path you will get a proof, okay, but you have to ignore where in some part you have to substitute 1, the same thing you have to do. Okay, so so this gives a randomized polynomial time algorithm for this. Okay, so I didn't formally explain what is randomized polynomial time algorithm, but you can, if you go back to this algorithm, you can see that this was an efficient algorithm, right? Because you didn't expand out the polynomial, you evaluated at a point. So gate by gate, you can actually compute these numbers. It's like a program for the polynomial is already given, program to evaluate. So you just have to carry that out, and that is efficient. And yeah, this algorithm may do mistakes, and that is why obviously the next question is, can you find a polynomial time algorithm that is like error free, the way you design deterministic algorithms, right? So that's a big open question. We do not know how to do it. Okay. Okay. Here is another. Okay. So can you reduce multivariate PIT to univariate PIT? This is another natural idea you may have thought, like dimension reduction, right? This n variate n dimension to one dimension. Can you reduce there? So basically, like here the idea is you can, in general, you can, like given a polynomial f x1 to xn, you can come up with another polynomial, say f hat x, such that f hat x is non-zero if and only if f of x1 to xn is non-zero. F hat x is non-zero if and only if f of x1 to xn is non-zero. How to come up with this? So basically, x1 you have to substitute to some polynomial in x. x2 also you have to substitute some polynomial in x, and xn also. How to achieve this?
Wouldn't something like x1 squared plus x2 squared something like that?
No. So the idea is like, so basically the idea for to achieve this is, so there can be n plus d choose d many multivariate monomials, right? And now in the univariate polynomial that you are coming up with, if you can achieve this, that each monomial you map to different degree univariate monomials, right? Then two different monomials would not be mapped to same univariate monomial, right? So if this thing is non-zero, then after the substitution also this univariate polynomial will remain as non-zero. Okay, so basically what I am saying is, like you have a x1 to the power alpha 1, x2 to the power alpha 2, xn to the power alpha n. This exponent vector alpha 1, alpha 2, alpha n, you have to map to an integer, and distinct tuples should be mapped to distinct integers. So you here also you know the idea how to achieve this. You probably know, right? So the idea is, like you basically, like suppose you assume these values of alpha 1 to alpha n, they are all bounded by d, right? Now can you use the DRE, like you treat this alpha 1, alpha 2, alpha n tuple as a number whose DRE expansion is this alpha 1 to alpha n. DRE expansion. Alpha 1 to alpha n, all these values are upper bounded by d. And if this is DRE expansion, then obviously, like all these for distinct monomials, distinct tuples, you will get distinct values, right? You are getting what I mean by DRE expansion. This is like, say, binary expansion where d equals to 2, ternary d equals to 3. So like that, okay. So these actually you can do like this. So basically what I am saying is, you have x1 equals to, you map it to x, x2 you map to x to the power d, x3 you map to x to the power d square, and so on. Okay, like in this way you can create this DRE expansion, and this. So this idea is known as Kronecker substitution. Kronecker came up with this map for a problem. But the price that you are paying, you can reduce to univariate, but this univariate polynomial's degree will be exponentially large, right? So univariate polynomial of exponential degree. So this also does not help in PIT, because obviously, like then this will polynomial have number of roots upper bounded by the degree, but that bound itself is exponential, so you cannot try out all those values. So another idea to modify this can be, like you pick W1, W2, Wn these are some rational numbers at random, and then substitute say t to the power w1, in x1 you substitute t to the power w1, in x2 you substitute t to the power w2, in xn you substitute t to the power wn, and these weights, they should not be exponentially large. You kind of like, you give pick weights from, give small values, and then you would also expect that this f evaluated at this, if original f was non-zero, then this will also be non-zero. Okay. And you can also prove this. Okay. So like Schwarzschild, here another very interesting and very useful lemma is used. This is called isolation lemma, due to Mulmule Vazirani. You can use this to prove this statement. Okay. So now I'll come back to this if I have time, but right now I would like to give you some applications of polynomial identity testing. So yeah, PIT probably sounded interesting problem to you, but like, are there other interesting problems that reduce to PIT? Okay, that is what you may. So one thing that maybe you have seen in like this string comparison, right? Or string equality testing. So if you are given strings like say 0, A1, AN, is it equal to say some B0, Bn? So basically, like, you can treat them as polynomials and test if these two polynomials are equal, right? This is the idea of fingerprinting, that actually, so the idea of fingerprinting. So there is an article that, sorry?
Is this similar to string hashing?
Yeah. This is in your, I think this is called string hashing, right? Huh? Yes, this is string hashing. You're right. So there is an article that actually I was checking if like the PIT is useful for competitive programming, and like the yeah. So there is an article like where to use and how not to use polynomial string hashing. You may take a look at that. Okay. So another application that is famous, that is primality testing. So some of you probably know about this result called primes is in P. Right. Have you heard about this result? So this is, so primality testing, obviously, like given n, you want to test if n is prime. And if you do brute force search, so n is given in log n bits, right? Roughly log n bits. So you have to, polynomial time algorithm has to be polynomial in log n, not n, right? So polynomial time. So if you try out, like say all the factors 2 to up to, you have to go till square root of n, right? So that will be like polynomial in square root of n, right? Like, so that is like, that is not considered to be polynomial time algorithm, because n itself would be given in log n bits. So this is like in 2002, 3 Indian computer scientists, Manindra Agarwal, Neeraj Kal and Nitin Saxena, showed that there is a polynomial time algorithm to test primality. So their algorithm running time was like log n to the power 6, around this. And before that, like I told you, randomized polynomial time algorithm for polynomial identity testing, there are randomized algorithms known for primality also. Okay. And the way they solved it, used polynomial identity testing in a particular way. So yeah, and these two authors like Neeraj Kal and Nitin Saxena, they were undergraduate students when they got this result. They were doing a BTech project under Manindra Agarwal, and yeah, so it's a like, and this result is very nice. You would be able to understand the proof also if you know some basic algebra like group theory and finite fields and all. Okay, so the why it is related to PIT, like what they tested is like if x plus a to the power n, is it congruent to x to the power n plus a mod n. Okay, n is prime if and only if this polynomial x plus a to the power n minus x to the power n minus a vanishes modulo n. It is identically 0 modulo n. Okay. But remember that, yeah, here also you cannot check by expanding out completely, because n itself, it is given in log n, so it is exponentially large exponent is here. Okay, so you cannot use the binomial expansion and test if this binomial expansion has only 2 terms, rest of the terms are all vanishing. Okay, so that is why you have to do. So yeah, in this case the idea is, so you have an exponentially large degree. How to reduce the degree? How to reduce degree? So one idea you can try out is, you can try to go modulo low degree polynomials. So you can try to divide by some low degree polynomials and test if the remainder is 0 or not. Okay. And if you take low degree random polynomials, then this will be true, not only for this identity but for any univariate high degree case. But in this case, they can eliminate the randomness, like which polynomials you have to take, like divide and take remainder, that explicitly they can describe. So okay, yes, so another application, and I will end with that, that is about testing perfect matching in bipartite graphs. So you know about bipartite graphs, right? So you have a set U, V of set of vertices. So suppose the coordinate of U and V are both n, and now given a bipartite graph, say matching is set of edges that do not have any vertex in common. And perfect matching means each vertex in the left hand side is matched with a vertex in the right hand side, and also the opposite. So this is like the yeah. So given a bipartite graph, how to test if there is a perfect matching or not. Okay. So this is the question. Given a bipartite graph, is there a matching? So probably you know about some algorithms for finding matching.
Seen
You
one.
have seen? Huh?
I
Okay.
don't remember.
Augmenting path based algorithms, have you seen? Uh-huh. Okay, so then let me, yeah, so there are like various methods to solve this problem. One particular solution involves this polynomial identity testing, and this goes about like this. So because I don't have time, let me give you the solution right away. So you come up with this matrix with u1, u2, un, here v1, vn. So the vertices in the left hand side are rows, vertices in the right hand side, they are columns. Okay. Now obviously, like if edge ui comma vj is present, then put xij, where x is a symbol, a variable in this matrix. Otherwise, you keep it 0. And say let us call this matrix M. So you can prove that there is a perfect matching in the given graph, in the if and only if determinant of M is non-zero. So this is not very hard to prove. Let me give you the idea why this kind of why this works. And yeah, then it boils down to you will get a again like the idea to test this whether this determinant is non-zero is again you substitute random values and check if that determinant is non-zero. Okay, because you cannot expand out this polynomial, right? This determinant will be a polynomial in this case, and use Schwarzschild lemma that for the okay the why so the idea is like you can relate matchings with permutations, right? Like say you have 1 to n, a permutation is like this is a permutation, so it maps 1 to some value from 1 to n, and so you have say for example like say 1 is matched with 2, 2 is matched with 3, 3 is matched with 1, right? So this matching described a permutation of 1 to 3. Right? So there is a definition of determinant. Determinant of a matrix A is you go over all possible, so it is n times n matrix. So you go over all possible permutations, all possible n factorial many permutations. So this set is called Sn. This is a group, and you take the sign of the permutation. Sign of the permutation is defined to be it is either plus 1 or minus 1. If the number of inversions is even, then it is plus 1, otherwise it is minus 1. So inversion is like if I is less than j, but in the permutation this is sigma is greater than sigma j, this is called an inversion, right? So then yes, you go over all possible permutation and you take these products and sum them. Okay. So there are how many permutations are there of 1 to n factorial many permutations. So there are n factorial many terms you will get for determinant. Okay. So these terms you can try to relate with matchings. Right. That is the idea.
Is this formula like does this have like is it called some lemma or something?
This formula of determinant. This is like, so there are various ways to define a determinant. In school, for example, the way you define A, B, C, D, A, D minus B, C, right? You use a formula to compute determinants, right? You go by row and then this statement. So this is another way to define determinants. So like if you search for, if you learn linear algebra from a textbook and search for definitions of determinant, then one of the definition will be this. In Wikipedia entry of determinant also you will find this formula definitely. So this is something obviously not very, it's standard in linear algebra. Okay, but then actually like I will end with just one remark. So just like you saw in the case of primality, here also you would like to, yes, so you saw in the case of primality I told you that there is a deterministic polynomial time algorithm that does not involve randomness, right? In the case of bipartite perfect matching, there are already polynomial time algorithms known that does not involve determinant. Still, we are interested in the solution where this for another reason, that is parallel algorithms. Okay. So you can imagine there are various processes, they can polynomially many processes, they can work independently, but they have to coordinate their work. So it's like, yeah, so there is a different model of computation in parallel setting. So for getting parallel algorithms for perfect matching, it is important to find a deterministic way to test this identity. Okay. And this isolation lemma that I mentioned before, that will also be useful there. Okay. So like till now this is an open question, like can you so the technical term for this parallel complexity class is NC. Like say P is the class for which you have efficient algorithms, NC is the class for which you have efficient parallel algorithms, and the question is bipartite matching, is it in NC? And this is not known. Using the idea that I told you before, it can be shown in randomized NC, and a partial de-randomization has been proven in quasi NC. Quasi means like there will be is like n to the power log n function. It is better than exponential, but it is not polynomial type. And this has been proven by Fenner, Gurjar and Thierhoff. So Rohit Gurjar is a professor at IIT Bombay. He has been involved in this work and some follow-up works. It's a very beautiful paper, like this result. If you search for bipartite matching in quasi NC, you'll get a paper, and it's a very elegant algorithm. So there is a funny, this was covered also in communications of the SEM. There was a title like, it said that isolating a matching when your coins go missing. That means that suppose, so I assume that I have random bits, right? I was assuming in this randomized algorithm that I can uniformly pick some things at random. But like, yeah, there is a whole lot of theory like why that's a fair assumption or something. But obviously like when you do not have random bits, still you would like to solve these problems. And it is expected to be, unlike P versus NP, here it is expected that every problem that has a efficient randomized solution, that can be like made into a deterministic algorithm, like there is a deterministic solution. And there is a reason, complexity theory reason behind this, why we believe this. Again, it has not been formally proved yet. These are the big open questions in complexity, P versus NP, and whether randomness gives any extra power. Okay. And what about the general polynomial identity testing problem? Yeah, there also we believe there is a polynomial time algorithm, but solving that, like if you find that, then that will be kind of very remarkable, because that will prove very strong lower bound results, not P versus NP, but some lower bound results regarding polynomials. Like I was telling you earlier that some polynomial, it cannot be computed using so many additions and multiplications. So you can prove some strong results about polynomials if you can prove if you can solve this question. Okay, that's all. Thank you.